I'm going to go through the process of getting from Ampere's law to the Ampere-Maxwell law. So we're going to start with what you might call electrostatics. So we would write the equations for this as divergence of E is equal to rho over epsilon naught. That's Gauss's law, which is very familiar. In electrostatics, we would write the curl of E is equal to 0. Now, of course, we know that's not actually true. We know that E can be induced by changing magnetic fields. So we're going to change that and we're going to put in a minus dB by dt so that we have Faraday's law. This was the result of a number of really very elegant experiments by Michael Faraday showing that the changing magnetic field did not depend on a change of current or a velocity. It's just the changing field from whatever source it has. So that's electrostatics, or now electrodynamics. We then have two laws which you can actually derive from the Biot-Savart law, which itself is empirical. The first one relates to the divergence of B, which, as we know, is equal to 0, at least as far as we are aware. We still haven't found any monopoles. And then finally we have Ampere's law, where we have the curl of B is equal to mu naught J. And Ampere's law is so named because Ampere really was the first person to postulate, to come up with the idea that magnetic fields were induced by moving charges. So this is the state that we had in around about 1850, before Maxwell did any of his work. And you can look at these, and at the time nobody had any problems with them. These were empirically derived laws, and in particular Ampere's law didn't seem to have any problems. However, we can identify problems with Ampere's law. Let's first of all consider a charging capacitor. This is a nice simple thought experiment that we can use to show that Ampere's law is not actually complete. Oops. So I'm going to draw the plates of the capacitor here. These are just vertical lines. I'm not going to try and draw it in 3D. We're going to have a wire coming from the left carrying a current I. We're going to have a wire going out to the right also carrying a current I, and over time we would accumulate charge, equal and opposite charges, on the capacitor plates. Of course, if you wanted to draw this properly as a circuit, you would need to have some source of electromotive force, a voltage or something like that, a battery. Now we're going to consider Ampere's law, but we're going to take it in the integral form. So I'm going to say we've got Ampere's law, and the way that we write it in integral form is as follows. It is we start with the surface integral of the curl of B dot n ds is equal to the surface integral of mu naught J dot n ds. So we need to specify a surface, and we're going to think about a couple of different surfaces. So I'm going to start off by creating just a very simple surface. So I'm going to draw a loop around the right-hand wire. So try and imagine that one is in 3D. So that's a loop which encircles the wire. And the first surface that we're going to think about, which I will draw in green, is going to be perpendicular to the wire, and it's going to be a flat surface which is in the same plane as the loop. We are going to have a second surface. Actually, let me put a label on that. That's going to be S1. We're going to have a second surface which is going to be that same loop as if it were blown out into an open bubble. So imagine the kind of soap bubbles you used to play with as a child. So you have a circle of plastic, you dip it into some kind of detergent solution. When you pull it out, you have a nice flat surface. When you blow into it, that surface billows out. And so I'm going to try and draw that here. Here is our surface which is billowing out, and that's going to be a sort of a half sphere, if you like, which I'm trying to indicate by these dotted lines, and that's going to be surface S2. And notice, please, that both surfaces are not closed. They're not closed, but both surfaces are bounded by that loop, which I am going to call C. So the loop that encircles the wire carrying the current is going to be called C. Okay, so now we've set up our situation, and we're going to use Stokes' theorem to transform the left-hand side of our equation. So Stokes' theorem tells us that we can transform a surface integral into a closed line integral. So we're going to have a closed line integral. I put the little circle around the integral sign to indicate that it's closed. And now we have B dot dl. So that's taking our magnetic field around the wire, but that's still equal to the integral over a surface bounded by C of mu naught j dot n dA, or ds I used before. And notice that S can be either S1 or S2, because both of those surfaces are bounded by the loop C. So if we are to use, let's say, S1, so let's do that in green, the surface is going to look just like this, and the current flowing through that surface is going to be I. So we'll say that the mu naught times the surface integral of j dot n ds is going to equal to mu naught I. Okay, we can see that because the surface is perpendicular to the current carrying wire. The total current flowing through the wire is I, therefore the surface integral of the current density J must be I. However, if we now consider the surface S2, which is this kind of bubbly fellow, like this, where the surface is all over here but not that loop, in this case there is no current crossing that surface. We have blown the surface out so that the wire does not cross through it. The surface encompasses the capacitor plate, so there is no current. So we would say that mu naught integral of j dot n ds, sorry, I should put an S1, now I'll put an S2, is going to equal 0. At this point, we realise that there must be a problem, okay, because Stokes' theorem tells us that those two integrals should be identical. So something must be missing in our physical law. In other words, Ampere's law is incomplete. Another way that you can think about this, if you want to, an alternative way of understanding that Ampere's law is incomplete, is to take the divergence of Ampere's law. I'm just going to write that as div. So what happens then? Well, we take the divergence of the curl of the magnetic field, and that's going to equal mu naught times the divergence of the current density. Now, the divergence of a curl is identically equal to 0. That's something that you can prove. However, we don't know what the divergence of the current density is. That's going to depend on the current density. So again, these two sides are not compatible. So the divergence of J will be equal to 0 if we have a closed loop. A closed loop of wire, or essentially if we have any situation where the current density is not accumulating, in other words, charge is not accumulating. So again, we have this problem where the two sides of the equation are not compatible. So I'll write that as div j is not equal to 0 in general. And if you want to think about that, you can just think about taking an integral of the divergence of j. And so if div j is equal to 0, that implies that no charge is going to accumulate inside that little volume you're integrating over, because the current flowing in will equal the current flowing out. And we know from the capacitor example, amongst many other things, that current charge can accumulate. So we're going to think about ways to fix this. So how do we fix Ampere's law? Because in many ways, in many experiments, it's very hard to actually detect the change, the discrepancy between the two halves of the equation. So we're going to turn to the continuity equation, and there's a video available on where the continuity equation itself comes from. Notice that you can in many ways derive the continuity equation from the Ampere-Maxwell law. So again, we've got a little bit of a chicken and an egg situation. This isn't a problem, it's just saying that these things are all compatible with each other and they're based on certain observations of the physical laws or the physical universe we're in. So the continuity equation is as follows. We say that the divergence of J plus d rho by dt is equal to 0. You can derive that, well, not really properly formally derive, but you can certainly obtain it by considering different definitions of current, and that's in a separate video. Now, noting that div j plus d rho by dt is equal to 0 suggests that there's an easy way for us to fix Ampere's law. So if we were to replace div j in Ampere's law with div j plus d rho by dt, we would know that the right-hand side would be 0. So that's one way that we could go forward. We could, of course, add any kind of curl to the right-hand side of Ampere's law, but that's not necessary. The simplest way of creating a right-hand side that is equal to 0 is to add d rho by dt, and it's often best to use the simplest possible approximation. We'll see that doing this leads to consistent physical laws. So let's do that. We're going to say that the div of curl B is equal to mu naught into the divergence of J plus d rho by dt, and that is equal to 0. So we now have a consistent equation. What would this mean for Ampere's law, or what we're going to call the Ampere-Maxwell law? Well, first we're going to note that rho is equal to, epsilon naught div E. And that fits very nicely into the equation. So what that implies is that our equation div of curl B is equal to mu naught into div of J plus epsilon naught divergence of dE by dt. You'll notice that I've changed the order in which I'm doing the different differentials. In this situation, that should always be a safe thing to do. And we can then, if we want to, change the right-hand side to put the J and the dE by dt together. And so what this suggests overall for the Ampere-Maxwell equation is as follows. You have curl of B is equal to mu naught J plus epsilon naught mu naught dE by dt. Please notice that this isn't a formal derivation of the law. It was simply a way of indicating why we add this time derivative of the electric field on the right-hand side. Maxwell originally wasn't actually thinking about this kind of symmetry. He was worrying about what they used to call the ether. This was a hypothetical medium in which electromagnetic waves propagated, which we know doesn't actually exist. So please don't think that this is a formal derivation. It's simply a way of understanding how and why this happens. Let's go back to our example of the capacitor and see whether this helps. So we're going to return to the capacitor. Remember, we had that the closed loop integral around C of B dot dl was equal to a surface integral. And now we're going to have to change this. This is going to be equal to the surface integral of mu naught J plus epsilon naught mu naught dE by dt. And that's going to be dotted with n ds, and that's going to be over the surface. Now, if we have, I think I used green, so we're going to have surface 1. If we take surface 1, that's the surface which is cutting the wire, then we would say that we're not going to have dE by dt, so dE by dt will equal 0. So the surface integral, the integral over surface 1 of mu naught j dot n ds is equal to I. Exactly, sorry, there should be a mu naught there, mu naught I, exactly as we had before. That's not changed. What about surface 2? Well, this is where we would expect to see the change because we've added something in. So for surface 2, we have no current density, but we may well have a changing field. For a parallel plate capacitor, we know that the electric field, and notice I'm not doing vectors here because we've not defined directions, we could put a vector in if we wanted to, is equal to sigma over epsilon naught, okay, where sigma is the surface charge, and if we have a total charge Q on the plates, that's going to be Q over A, the surface area of plates, times 1 over epsilon naught. So the time derivative, dE by dt, is going to be dQ by dt, and notice that I've gone from a partial differential for E to a full differential for Q, because Q is only a function of one variable, multiplied by 1 over epsilon naught A. dQ by dt, of course, is just the current flowing in, so this is I times 1 over epsilon naught A. If we then integrate, so we're going to do the integral over S2 of epsilon naught mu naught dE by dt dot n ds, that's going to equal epsilon naught mu naught. The integral of dE by dt over the area is going to simply pick up the entire field, which we'll assume is constant, and multiply it by the area. So we're going to have I over epsilon naught A, that's the dE by dt part, and then the area integral is going to give us an A. And you can see that the A's cancel, the epsilon naughts cancel, and we have mu naught I. And so in this case, the two sides, the two surfaces now match. And we have fixed Ampere's law. Of course, this demonstration is no proof, it's simply an indication that we have done something sensible. We know that the Ampere-Maxwell law is compatible with the rest of electromagnetism, but this is now a way that we can understand where those links come from and how that changing electric field fixes the problem for the capacitor.